principle to calculus than limits, and with limits the principle of continuity. In fact, calculus works through the principle and use of limits. Now we're going to examine the concept of limits verbally, graphically, numerically, and analytically or algebraically. In pre-calculus class you may have studied limits like this in function f of x equals e to the power of x. What we looked at here was limits as x goes to infinity and to negative infinity. As the input values increase, the output values increase. In fact, these values increase exponentially. When people talk of increasing exponentially, most of the time they are speaking figuratively. What we're looking at here is the real thing, literal exponential increase. And we were introduced to the limit notation, which is the limit as x goes to infinity of f of x is equal to infinity. And we can also check out the limit in the other direction as x approaches negative infinity. As x goes toward negative infinity, the output values approach the x-axis. And here's the limit notation. We say that the limit as x approaches negative infinity of f of x equals 0. The function value never does actually touch 0, but its limit is 0. Another way of saying this is that f of x has a horizontal asymptote of y equals 0. But in calculus we're interested in the limit of a function as x values approach real numbers somewhere in between negative infinity and positive infinity. Here's a more zoomed in view of the same function f of x equals e to the power of x. We're going to find the limit of the function f of x as x approaches 1. And here we have a dotted vertical line at x equals 1. For this limit we're looking for the output value, or the limit as x approaches 1 of f of x, here shown in limit notation. To have a limit as x approaches a real number requires the limit from the left side of the x value to equal the limit from the right side of the value. And graphically we can see that there is a limit because the left side of the function meets up with the right side of the function at x equals 1. We can visualize the input value being assessed or evaluated for a limit as we would a fence, in this case a vertical fence. If these two sides of the function, from the left side and from the right side, approach the same point in the fence, we say that the function has a limit for, in the case of f of x equals e to the power of x, an x value of 1. And here's the situation in limit notation. We have the limit as x approaches 1 from the left side. That negative sign to the upper right of the 1 means from the left of the function f of x equals the limit as x approaches 1 from the right side of f of x. If the two sides of the function do not meet up at the fence across from each other, we say that the function has no limit at that input value where that fence is located. In this situation, we say that the limit as x approaches 1 from the left of f of x does not equal the limit as x approaches 1 from the right side of f of x. So we say in this notation that this function does not have a limit where the x value is 1. Now back to our function f of x equals e to the power of x. Since the function is continuous at x equals 1, we know that the limit as x approaches 1 from the left side of f of x equals the limit as x approaches 1 from the right side of f of x. One important thing to point out here is that if a function is continuous at a value of x, that function has to have a limit at that point. And the value of this limit is the y value, or output value, of the function at this point where x equals 1. We can see by drawing a line segment horizontally to the y-axis that the value of this limit, which we see labeled capital L, is between 2 and 3, a little closer to 3 than to 2, maybe about 2.7. This would be a graphical evaluation of a limit. Our understanding of what this limit is limited by the accuracy and scale of the graphing. Next, numerically, we can look at input values approaching the x value of 1 from each side, from the left side and from the right side of 1. We can see as we go from inputs on the left side of 1 of 0.9 through 0.999 the outputs get closer and closer together as well. And from the right side, the value at the top closest to 1 is 1.0001. So these output values, while not exact, are going to be very, very close to the actual limit in this function as x approaches 1. As we get closer to 1, we will get closer and closer to the limit, which will improve in accuracy as we use more and more decimal places. From the left side, the closest value we have to the actual limit is 2.27180, and from the right side, the closest value we have to the actual limit is 2.7186. With this information, we could split the difference between these two values and project a limit of or close to 2.7183, which is the average of 2.7180 and 2.7186. Now we'll evaluate this limit analytically. The function is continuous at x equals 1. Therefore, we can plug in 1 for x to evaluate this limit analytically. F of 1 is e to the power of 1. So the value of the limit, or capital L, is Euler's number e, which is approximately 2.718281828. And this is pretty close to our approximation from the tables of 2.7183. Now we're going to look at limited domain functions. The three precalculus parent functions that have limited domains are the logarithmic function f of x equals ln x, the square root function f of x equals the square root of x, and the reciprocal function f of x equals 1 over x. What we're going to focus on is this function on the bottom, the reciprocal function, which is what we call a rational function. Rational meaning that the variable is located within the denominator of the function, of the fraction. Most, though not all, rational functions have a break in continuity. Specifically, any value of x that makes the denominator of a fraction equal to 0 is an input value where the function is not defined because division by 0 in mathematics is not defined. Honing in on rational functions, we'll first look at the function f of x equals 2 over x minus 3. In this case, the function is not continuous over its domain and has a discontinuity at x equals 3. Since the output value of the function goes down as x approaches 3 from the left side, we say that the limit as x approaches 3 from the left does not exist, or in other words, that value approaches negative infinity. And from the right side, the limit as x approaches 3 from the right side of f of x does not exist and goes toward positive infinity. This type of discontinuity is called an infinite discontinuity or a vertical asymptote. Now let's look at this rational function f of x equals 2 over x squared minus 4. For this function, the limit as x approaches 0 from the left of f of x equals infinity, and we can say that the limit as x approaches 0 from the right side also equals infinity. But even though the limits from the left and from the right both equal infinity, still the limit does not exist because limits from the left side and the right side need to equal each other, and that equaling need to be a common real number, and since infinity is not a real number, the limit does not exist for an input value of 0. So our notation is that the limit as x approaches 0 of f of x is infinity or does not exist. Even though the limit is infinity, still that limit does not exist because the limit does not approach a single real number from each side of 0. Infinite discontinuities like this one can also be called non-removable discontinuities. Here's another rational function. We have f of x equals x squared minus x minus 6 over x plus 2. We will find the limit of this function at x equals negative 2, that is, if the limit exists. Here's a vertical line at x equals negative 2. It looks like for an input value of negative 2, we get an output of y equals negative 5. But we know, or should know, that the denominator of the function equals 0 when x equals negative 2. And that means that in spite of the graph of this function having every appearance of being continuous, the function is not continuous at x equals negative 2. We call this break in continuity a point discontinuity, a removable discontinuity, or a hole. This discontinuity is represented graphically by an open point. Every point on the line is included in the function except the point where x equals negative 2. That's the meaning of the open point, which is represented by a small open circle. It's easy to see why we call this a point discontinuity or a hole, but why do we also call this hole a removable discontinuity? It's called a removable discontinuity because if we factor the quadratic trinomial in the numerator, we get f of x equals quantity x minus 3 times quantity x plus 2 over x plus 2. X plus 2 over x plus 2 cancel each other algebraically to equal 1. And we're left with f of x equals x minus 3, except that it's not really x minus 3 because this function has a discontinuity at x equals negative 2. This function behaves exactly like f of x equals x minus 3, except at the point where x equals negative 2. So that's how we get the hole in this function. So the discontinuity is removed algebraically. That's why we call this a removable discontinuity. Here's a numeric representation of this function. We can see that for an input value of negative 2, we get an error message in spite of the graphed line appearing as the function f of x equals x minus 3. However, there is a limit as x approaches negative 2 from the left side of f of x, and that limit is negative 5. And the limit of f of x as x approaches negative 2 from the right side of f of x is also negative 5. And in limit notation we say that there is a limit because the limit as x approaches negative 2 of f of x from the left side of f of x equals the limit as x approaches negative 2 from the right side of f of x, which equals negative 5. Yet for an input value of negative 2, f of x is undefined or does not exist. So the limit at x equals negative 2 exists and equals negative 5, even though the function is not defined and is not continuous at x equals negative 2. So far in this lesson, we've looked at functions that operate under just one function rule or equation. Now we'll look at functions that employ different equations or rules depending on the input values. That's what we call a piecewise function, a function that uses more than one function rule or equation. This is an example of a piecewise function. This function has two pieces, f of x equals x squared minus 2 for x less than or equal to 1, and 2x for x is greater than 1. Let's evaluate this function for continuity where x equals 1. These commas in piecewise functions translate verbally to the words when or where, also possibly the words for or if. To see what's happening in a piecewise function, we look at the graph of the two separate pieces. The first piece of f of x is y equals x squared minus 2 graphed here on the left. And then we have the function y equals 2x just to the right. In a piecewise function, this piecewise function, we use the equation y equals x squared minus 2 for input values of less than or equal to 1. And for the y equals 2x piece, we're only using this function for values of x greater than 1. A piecewise function puts these two pieces together on one graph. And here they are, both pieces put together as the single graph of f of x. Visually, graphically, we see that this function is not continuous at x equals 1 because of the jump between the two pieces. This is what we call a jump discontinuity. But analytically, we write that the limit as x approaches 1 from the left side of f of x equals the limit as x approaches 1 from the right side of f of x. And since we haven't yet calculated these limits from each side, we write the equation with a question mark above it. For this function, the limit as x approaches 1 from the left side of f of x is negative 1, and the limit as x approaches 1 from the right side of f of x is 2. We can summarize with the inequality negative 1 is not equal to 2. So therefore we conclude that the function f of x is not continuous at x equals 1. Let's look at another piecewise function. G of x equals 2 when the values of x are less than 2, and x squared minus 4x plus 6 where x is greater than 2. Let's evaluate this function for continuity where x equals 2. If you know or remember one thing we need for continuity, we could quickly evaluate without graphing or finding limits, so that would save us the fun of graphing this piecewise function. For this function, we'll plot both pieces on a single graph. First, we graph the piece that's for x values of less than 2. Next, we plot the piece that's for x values greater than 2, and that's g of x equals x squared minus 4x plus 6. Looking at the graph, there's a point discontinuity at x equals 2 because the function is not defined at this point. Since we have a less than 2 and a greater than 2, this means that g of 2 does not exist. So even though the limit as x approaches 2 from the left of g of x equals the limit as x approaches 2 from the right side of g of x, which equals 2, this function fails the test for continuity because the function is not defined at x equals 2. So to sum it up, this function is not continuous at x equals 2. So at the beginning, before graphing and otherwise evaluating, we could have noticed that g of 2 did not exist and therefore could not have been continuous where x equals 2. Let's look at one more piecewise function. H of x equals negative x plus 7 for values of x less than 6 and 1/2 x minus 2 where x is greater than or equal to 6. The instruction is to evaluate for continuity at x equals 6. Here's the left piece of the function graphed. There's an open point at x equals 6 because this piece is for values of x less than 6. And here's the piece on the right side that's graphed. At x equals 6, there is not a gap in continuity. And analytically, we would write this evaluation as the limit as x approaches 6 from the left side of h of x equals the limit as x approaches 6 from the right side of h of x, which equals 1. So in conclusion to this problem, h of x is continuous at x equals 6. Let's summarize what elements are needed for a function to be continuous and how to determine if there is a limit. And for that summary, we'll consider the graph of the function f of x. At an input value of a, we have no continuity because of the point discontinuity there represented by the open point. But since the limit of this function from the left side of a and from the right side of a is the same and appears to be negative 2, we say that there is a limit of negative 2 for an input value of a. Now for an input value of b, we have an infinite discontinuity or vertical asymptote. The function is not continuous for an input value of b. And the functions never meet across the fence. They get closer and closer, but not at a single value. There is no limit, or the limit does not exist for an input value of b. For an input value of c, we see no break in continuity. So f of x is continuous at x equals c. We can also see that there is a limit because the value of the function as x approaches c from the left side and from the right side is equal to 1. For an input value of d, there is no continuity, nor is there a limit. Likewise, for an input value of e, there is no continuity because of the jump discontinuity. Also, there is no limit because the limits from the left side and from the right side are not the same. For an input value of f, the function is not continuous due to a point discontinuity, but there is a limit since the same value is approached from the left side and from the right side, and the value of that limit is 2. We can represent the relationship between limits at input values and continuity at those same input values using a Venn diagram. We'll consider the universe of input values where limits exist. And inside of this universe where limits exist, there is a subset of input values where there is continuity. To summarize the relationship, wherever there is continuity, a limit must exist. But a function may not be continuous everywhere there is a limit. For example, in these instances of continuity and limits we just went over, a through f, The only input value where a function is both continuous and has a limit is c. But the input values of a and f each have limits without the function being continuous at these values. Let's summarize what elements are needed for a function to be continuous, and for that summary we'll consider the graph of the function f of x to the right. We'll consider the input value of c. In order for a function to be continuous at a certain input value c, first f of x must exist where x equals c. Secondly, the limit of the function must exist at x equals c, and in more detail, the limit from the left side of c and the limit from the right side of c must be equal to each other. And finally, that limit at an input value of c, which we call capital L, must be equal to f of c. We need to have each of these three requirements met for a function to qualify to be continuous for a certain input value of c. This has been Limits and Continuity. Thanks for viewing.